Good morning, developers. If you are new to the channel, my name is Rob, and it is CS Thursday, the day that we put our keyboard away. We're not going to code. We're just going to look at some computer science concept, computer architecture, what makes programming languages work. It's sort of the day that we, if programming is electricity, that we become physicists and stop being electricians, at least for a minute. And the question we're going to try and answer today is, why is there a hexadecimal system? Who on earth thought that this was a good idea to represent a number with the letter E or the letter F? It hurts my head whenever I've seen it. And at the very least, you probably have seen it in CSS. It's how we represent color. And why are we asking this question? Well, if you found this video via search, then you have your reasons. If you're a subscriber, it's next in line. Why am I going to explain this to you? It has meaning under the hood in a big way. And I will say that having been an engineer for 20 years and worked with every type of developer, really one of the key differences between the good developers I've worked with and the great ones are knowing how and why things work. And that's absolutely what we're looking at here. I did another video, and I can link it in the description. It happens to have been last week. But we talked about why computers struggle with doing 0.1 plus 0.2. It doesn't equal 0.3. And we're going to kind of stay in that same vein. The reason is because of binary fractions. The hexadecimal digits really come down to binary, okay? And I will get there, but give me just a second. If we were to define a computer, and we did this in the other video as well, but if we were to define a computer in the simplest terms possible, without any more presuppositions than we absolutely have to make, how would you define it? The way I would define it is that a computer is a big state machine. And that's it, right? In spite of all the awesome software there is, in spite of what AI is moving towards and so on, it's really just a ton of little light switches, right? All a computer is this. And no, that's not a 0 and a 1. It's a gate, it's a voltage gate that's closed and one that's open. It's electricity that's not going anywhere and electricity that is. That's what a computer knows, is when electricity is moving around. We associate the off with the number 0, and we associate on with the number 1, or binary, right? That's what computers are based on, the two-base system, the zeros and the ones. And again, you have trillions or quadrillions of little light switches that a computer can know basically what state all of them are in at almost the same time, and it can change all the switches almost, again, instantaneously. So that's what makes it such a miracle. But it's really, really simple. It's really just a bunch of light switches, and we represent the number 0 with off, and we represent the number 1 with on. So in terms of computer architecture, we call this, when we store it, a bit. That's the smallest possible thing that a computer understands, is a single digit or single on-off. That is a bit. But that's not the basic building block in storage, at least that we usually refer to. Typically, we refer to a byte. And a byte is 8 bits. So you can think about it like this. We have a little piece of storage, whatever it is, and we've got there 1, 2, 3, 4, 5, 6, there we go, 8 little slots for an on or an off to go, a 1 or a 0 to go. So that means you can make any number that this will hold, and that happens to be 2 to the 8th power minus 1. So that's the biggest number that we can make. If we had a 1 in every single slot here, we can make between 0 and the number 255. That's the max number we have. So we can make 256 total combinations in one byte, okay? Why 8? Now, why 8 and not something else? There's potentially lots of reasons for that, but I will give you at least a few. Back when Intel started making their processors, it went like this. They made the 8800 series, and that was an 8-bit CPU. We bumped up to the x86. I think it was actually 8886 maybe, but those were 16-bit. And then we got to the 386, or actually 386, and those were 32-bit. And now we are currently on i7s and i9s. Who knows, by the time you're watching this, maybe there's i11s, but those are 64-bit. What does the bit mean? Well, when you store something in a memory register, the CPU, like the memory register built directly on the CPU, and they are fast, like really, really fast, because the processor stores stuff there and can get it basically instantly for all intents human purposes. We use them all the time. Now, as a JavaScript or Python developer, you have no idea what I'm talking about. That's because Python and JavaScript is doing it for you, but we're still using them. We're doing it, or our language, I guess, is doing it behind the scenes for us. The bits here, this is the biggest possible number or binary digit that you can store in one of those memory registers. So it's 64 bits if it's a recent CPU, or it's 32, or it's 16, or it's 8. Do you see a common theme there with those numbers, right? These are all factors of 8. This is 1 byte, this is 2, this is 4, and this is 8. It circles around this 8-bit concept. So the architectures have just followed this pattern. The next computer, the next size architecture we need would be 128-bit. And I can imagine that's necessary, because a 64 unsigned digit is like 19 quintillion. I'm sure it'll come when we need more, but it's hard to imagine. But that is at least one reason, okay? Another reason, our color spectrum. I already mentioned this. If you want to make the color black, it's 0, 0, 0, 0, 0, 0. 0, 0 is the first part is how much red. The second is how much green. And the third is how much blue. If you wanted to make all white, you would do F, 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 FF, okay? We're getting to that. But this would be maximum part red, max green, and max blue. 256 is what this number represents all across the board. So we have between 0 and 256. That gives us, you might have heard the term before, but 16.8 million different shades that we can use with this system. And again, these are bytes. This right here is a byte. It represents 256. Same thing here. That's another byte, and that's another byte. It takes 3 bytes to represent almost any color that most monitors can use. 8 is also the building block for our storage system. We don't refer to how many bits there are on a hard drive. You say, I have a 1 terabyte hard drive. We're up to petabytes. Probably pretty soon we'll have exabytes. But again, you get the idea, okay? 8 bits makes 1 byte. And 1 byte is the absolute cornerstone, the building block behind almost all computer storage architecture, okay? Enter the hexadecimal system, okay? Let me clean this up real quick. I'm going to mention one more case for why we use 8 bits. If you want to type the letter A and you want to store it, okay, to a computer, there is no A. There aren't ones and zeros. There's just ons and offs, right? But we store it in the concept of binary. We use the ASCII system, and you can Google ASCII chart or something, and it will show you all the ASCII values. But in binary, the letter A is this. It's 0, 1, 1, 0, 0, 0, 0, 1. That equals the letter, the small a, okay? You can make pretty much any character on your keyboard with a single byte. It is an 8-digit binary number. All right, and if we total this up quick, okay, we're out here. This is the 128 place. This is the 64. So we have 64 plus 32 plus 1 equals 97. So what we have here in decimal is the number 97. But that is really ugly. I don't want to look at that. I don't want to think about the letter A and try and remember how many zeros are there again before I get back to a 1 or whatever. Computers are good. They're awesome at that. Don't get me wrong. But we can do a 1 better here, okay? How many possibilities did we say there are in this 1 byte? These 8 bits that we have here. It was 2 to the 8th power. 2 to the 8th power because we have 8 slots and there's only 2 digits per slot. All right? So there are 256. I'll put that up here. Do you see a relationship here between these two numbers? That's how many digits we have over here, 0 through 15, right? Or rather 0 through F. Do you see a relationship here that is special? There is one. Okay? 256 is the same thing as 16 squared. We were working down here with 2 to the 8th. Here we're working with 16 to the second. Why? There are 16 digits. We can represent this entire byte with hexadecimal with just 2 digits. So instead of looking at this ridiculous thing, what we do is we can grab these in pairs of 4. Okay, so 0, 1, 1, 0. What does that equal? Okay, so 0 and 1, that's 2. This is the 4 spot, so this is 6, what we have here. So what's actually here in hexadecimal is the number 6. What's the number here in hexadecimal? It's the number 1. 61 is what the A is in hexadecimal. That's awesome. I can get excited about that. I don't like that. Okay? That is the answer to our question. What is the point of the hexadecimal system? It is a really, really, really nice way if you're a human having to look at machine code, right? Zeros and ones, and you want some in between, right? You can't actually go to your normal numbers, your normal decimal system. You want those something in between that's not so ugly as this. Bam! The hexadecimals are the answer. And we can do that with however many bytes there are. You can always represent it with 2 hexadecimals, and it's really, really fast. I'm going to put up here an arbitrary number. Okay? This happens to be, 64 and 32. So we're at 64 plus 32, and then we've got 8, we've got 4, and then we've got 1 at the bottom. Okay? So in decimal, this is 96. That makes 100. This makes 109 is what we've got there. Okay? At least I think it is. We can cut this up into 2 pieces. Instead of having to do all this math that I just did, which I didn't like doing, okay? Instead, we can go, okay, 0, this is 2, this is 4. Okay, so the number we have here is 6. And the number we have over here, well, this is 1, that's 2, so 4 and 8. So 8 and 4 is 12. This is 13. Well, we can't write 13. What's 13? D. What we have here is 6D. That took almost no time, right? And if you get really fast, I'm taking longer to do the binary than necessary, but if you get really fast, you can start representing massive chunks of bytes really, really fast. So we'll do it one more time here. We'll have 0, 0, 1, 1. So this is our first 4 bits, and the second 4 bits are going to be 1, 1, 1, 1. What is that in binary? Or what is that in hex? Well, we're sitting on 3, so it's going to be 3. Over here, we're sitting on the max that we could possibly hold, which is 15, or F. That's 3F. I could have done that in my head because I've seen it enough. With a little bit of practice, you will too. But again, that's why we have a hexadecimal system. Because we're working down here. If you have a memory dump, the blue screen of death in the old days on a 64-bit system, if you were a C programmer and had to look at the memory dumps and stuff, you don't want to see a 64-digit binary number. It's so much easier to break it up into just 2-digit chunks, and that is so much easier to digest. So this is our in-between. Computers only understand on and off. Okay? We have them so that they can represent at least binary to us. But as programmers, we don't want to look at binary. And we can't jump over to decimals. We have the hexadecimal system to stand in place, right? For the colors, for our architecture, for our key values inside our keyboards, and so on. Okay? Thanks so much for watching. I will link another CS Thursday video. I will catch you next time.